Today we will be discussing fundamentally how RAG is able to fetch related documents based on meaning or based on similarity. We will try to understand the core functionality of how the RAG fetches it. But before we start with that, I'll quickly try to give a quick overview of what we are talking here about. So we are talking about the whole RAG flow, right? And here, let's say you have n number of documents here, and the user asks a prompt, right? And in the RAG system, what you do is you first embed the all the documents in a embedding using a embedding model, and these are saved as vectors in a vector space. So let's say each of these documents are placed at these different locations, right? And then the user asks a prompt. And what happens is this prompt is also converted into an embedding or a vector using the same embedding model, right? Let's say this embedding model has 1024 vector spaces, and each of those spaces have weights. And then finally, you have to figure out, okay, where this prompt sits in this whole vector space, and you need to find out the nearest document. So for example, if the prompt sits in this position, you need to think like, okay, this is the nearest one, this is the second nearest one, and this is the third nearest one. So 1, 2, and 3 are containing data related to this query, and all these documents are then passed to the LLM for the LLM to give an appropriate answer. So this is the whole workflow that we are trying to understand. Now the question comes, okay, now you figured out that this embedding vector sits in this position. Now how do you actually find which one is this nearest? I mean, you are looking at the screen, you might think, okay, this is near, but mathematically, how does this happen? How do you figure out which are these documents that are the most nearest in the vector space to this prompt vector, right? So this is where the method called as cosine similarity comes in. What is cosine similarity? Cosine similarity is basically the angle between the prompt vector and the other vectors that you want to figure out. So if the angle is less, it means that they are similar in nature. The other metric is Euclidean distance. Euclidean distance is how far away are these two vectors in the coordinate space. So what is the distance? That is one metric, and what is the angle? So these are the two metrics that we use to figure out, okay, which are the nearest documents. So now if you look again in this picture, right? So there can be two things. One is Euclidean distance, so distance between this point and this point, distance between this and this and this and this, right? The other thing could be angle, right? So let's say, okay, maybe here this is not clear. Let's take this, and this document, for example. If you look at them, they have similar angles, right? So if the prompt vector was this document here, so these two documents would be very near in terms of angle. And then the next one would be Euclidean distance, and then you would do a summary of both of those, and you could take the top three documents. So this is the whole idea that we are trying to explore today. Okay, so let's have a look at cosine similarity, how the function itself is calculated. This is also part of the course that we are doing, and here you can see this function in one of the unassigned or one of the other examples that are there. So basically, you have two inputs, right? So one is this array of vectors, which is basically all your documents. So you pass all your documents inside this function and say, and then you pass your prompt. So these are the two inputs. So your V1 is your prompt, and the array of vectors is all the other vectors that you want to compare, and you want to find cosine similarity with this. Okay, what happens is first one you convert this V1 into NumPy array. Okay, why do we do this? Basically, NumPy array or a normal array, what is the difference is NumPy is um, actually optimized for speed. So basically, any mathematical calculation you want to do on a set of data, right? So NumPy is faster. let's end it there, because then if we go into that details, then it will take a lot of time. So NumPy we convert because it is faster. Okay. Now we want to create a similarities vector where you calculate the value of the similarities and you pass it back from the function, and then later you compare it with v1, and then okay, so if the similarity is high, then the result is nearer to 1. If the similarity is low, the result is nearer to -1. So this varies between 1 and -1. Okay. Then you check if the array of vectors is a single vector or not. So why do we do this check? If the array of vectors, or basically in this array of vectors, if only one vector is passed, then what could happen is, instead of comparing it with the entire vector, you could end up just comparing with uh, the individual scalar numbers. This can be a bit confusing to understand. So what I'll do is I'll quickly try to explain it with a diagram here. Let me connect it. So let's say you have to compare two different vectors, right? So each vector is, let's say, I told in our example, the vector space is 1024, right? But here for simplicity, let's say our vector space is of 3 bits. So 0, first and second bit, right? So let's say you want to compare uh, these vectors with another set of three-dimensional vectors. So if you do this comparison, it's fair, right? But what happens is, if you just pass one vector instead of passing multiple set of vectors, so then what happens is, then what in the calculation, what happens is you end up passing this individual values for comparison with an entire vector, which is wrong. So let's say 5, 7, 9, right? So if you have to compare, if you just pass one vector, you will end up passing this single digit, because then here these are the commas. So here it will take this entire entity as one and then pass it to comparison with 1, 2, 3 versus this. So comparing these two are okay. But now if you just pass one, so what it will do is, it will take the entity one and then it will try to compare with 5, 7, 9, which is wrong. So what it basically does here is, in this, it just adds another block around it. So it's a very simple thing. So basically, it does like this. So something like this. So now when you go into iteration, now it knows, okay, this is the lowest entity and this is the only one. So basically, you add another square braces around the single dimensional vector. So it's a simple problem, but yet still needs to be solved. So that is the check if any vectors is a single vector. So then you add a square bracket around it, so that when you pass it for this for loop, then that entire thing is passed into this v2 for comparison. Okay, so that's the check. And now you take the array of vectors and you have to iterate it one by one. Okay, so now you basically compare v1 with v2. So each of the prompt you have to compare with the individual set of vectors. Again, you do the NPy thing because, yeah, okay, it's faster. And then you have to do a dot product. Dot product is basically a matrix multiplication where the elements of these array are multiplied and added. It's a matrix multiplication thing. So to get a scalar value at the end of the day, so you do, I don't know, so maybe I can quickly explain this again. So if you have something like 1, 2, one vector, and then I don't know, 3, 4. So you do 1 into 3 plus 2 into 4 is equals to 3 plus 6 and equals to 9. So you get a dot product. Uh, so I'm not sure if I did this exactly correctly how it's supposed to be, but at the end of the day, you get 9 as the solution as a dot product. So that is your dot product, and then you normalize V1 and V2, and then the formula to calculate similarity is dot product divided by normalization of V1 by V2. Okay, now what's the whole idea behind this calculating the dot product and the normalization, right? So let's try to understand both these. So what is the meaning of dot product? What does it signify, right? So wait one second, sorry, norm, and this is the dot product. Okay, so with the dot product, basically what we are trying to do is we are trying to calculate the angle, right? So when we first started out, we wanted to calculate the angle between the two vectors and the corresponding thing. So this cosine similarity is basically helping you find the angle. We are okay. This Euclidean distance has a different formula, but right now we are discussing the cosine similarity. And the cosine similarity formula is basically dot product divided by the normalized values or something like this. So, okay, first is dot product, and in the dot product, what is the value of that scalar, right? So, let's say if it's a positive value, um, it means that the vectors point in a similar direction. That is the meaning. That is the meaning of it. If it is zero, then the values are perpendicular or like in 90 degrees. If it's a negative value at the end of the day, then it means that they are opposite in direction. So these are the reasons why we calculate the dot product. So okay, it actually signifies the angle based on the numbers. Maybe the numbers were negative and then you got a negative number, and then at the end of the day, the angle became obtuse because the numbers were different values. And okay, the second part of it was basically to calculate the normalization. So normalization. So let's say, for example, you have a vector 3 and 4. So what is normalizing is basically you do a square, and then you do a square root of. You basically nullify the negative part, and then you do a square of those values, and finally add them up, and you do a square root of thing of this, and you get this value, and then you divide. You divide the dot product divide by this product of the normalized values of each of this, and then you finally get the similarity. And then this similarity, if it lies between if it is 1, if the similarity at the end of the day, the value that you get, if it is 1 or closer to 1, it means that the angle of these two vectors are in similar direction. So this is the similarity. If the value ends up to be 0, then it is like 90 degrees, which is again not so great. They are in opposite direction. And okay, if it is closer to -1, these are in opposite direction. So no similarity. So we have to pick up the values that are near or similar. So again, if we try to again find this, so in the normalization gives you the magnitude, the distance between 0 and the endpoint, and the dot product gives you a scalar value, something like this. So this is exactly what I was trying. 3 into 5 plus 4 into 1 equals to 15 plus 4, 19. So based on these values of this dot product. So that is the dot product again divided by the magnitude, and then you get a value between -1 and +1, which is basically your cosine similarity. So based on this cosine similarity, you can figure out which are the documents that are in a similar angle. So similar angle. And similarly, we have another method for Euclidean distance. I did not again think, okay, we'll discuss again the same function. It is something similar. It has its own formula. So based on this formula, what we do is we iterate through all the arrays of vectors that are passed, and then you calculate the similarity, and whichever is similar, again, the value is between 1 and -1. So then you pick up the documents that result in 1. So whichever is 1, and then you decide to pick how many nearest you want to pick. Do you want to pick 3? Do you want to pick 5? And based on that, you pick those documents, and then you pass to your LLM, and then the LLM looks at the data within your documents, and then it can answer better. So you have to then figure out, okay, based on the context window of your LLM, do you want to pass 3 documents? Do you want to pass 7 or whatever? So that is your whole idea behind this finding the nearest document. So these two are very essential metrics, and I think it helps to, I mean, understand what these are and how these are implemented. But fundamentally speaking, you basically try to find either the distance or the angle between the vectors. You can either use a summation of both, so you bring both the values together, and then you try to figure out, okay, which one of these are makes sense for you, or you can just use cosine similarity based on how this feels better for the particular application. So this is about cosine similarity and Euclidean distance.